All right, let's go ahead and get started. So if you haven't already seen, the grades for the test are, come on. They're in Canvas. I have a couple more people who need to take it, and then I'll hand those back to you. In the meantime, if you want to schedule a meeting with me to talk more about it, we can definitely do that. If you didn't see my announcement this morning, there's I think a really valuable tool that one of the other instructors put together to help you practice for the mastery test. So I posted a link to that in the announcement and in that exam prep module on Canvas, but I would really advise taking a look at that before next Wednesday. Anything else about what's coming up, or any questions about anything before we go? All right, here we go. So continuing on with chapter 4, section 3 is about derivatives and what they say about the shapes of graphs. So, just looking back, what does the derivative tell us about session? So the slope of a tangent line. Anything else? Okay. So slope of a tangent. Instantaneous rate of change of a function. Anything else we've talked about in relation to derivatives? Can I say anything about the derivative? So I've got a graph of a function here. Can I say anything about the derivative, at any particular point or interval, or what might the derivative tell us about this graph, or what would be true about the derivative? Okay, so in this case, where would the derivative be equal to 0? So you agree with those three places? Anywhere else where the derivative might be equal to 0? So one thing you said the derivative has to take place at minimums, maximums, things like that. If the derivative is equal to 0, does that point have to be a minimum or a maximum? I think on this graph it does, but in general, absolutely not. So in general, you can have the derivative be equal to 0, but you might have what we call a saddle point. So pretty good at looking at, finding those places where the derivative is equal to 0. For example, let's look at something else. What can I say about f prime of 1? Why is it negative? Okay, slope is downward, right? What's the function doing there in one word? It's decreasing. Is there any points on here where you could say the derivative is positive? Be 4.5, so actually let's make it easy on ourselves. For example, f prime of 0 is positive, right? So we kind of understand what the first derivative tells us about a function, or if I look at a graph of a function, I can draw some conclusions about what the first derivative might be. Any questions on anything we did right here? So part of this section, we're going to look deeper using that first derivative to learn things about functions. We're also going to look into the second derivative and what that tells us. So one thing we just looked at was increase and decrease, and something I think we've thought about quite a bit before, but just a reminder here. If your derivative is greater than 0 for all x on an interval, then f is increasing on the interval. Or it doesn't have to be an interval, it can just be a point. So very similar idea for decrease. And let's just hammer this point home. If f prime of x equals 0, what does that say about the function? What's the function doing? What was that, Tom? So I'm going to write it the way you said it. You said constant, like a question. Is that okay to say that the function is constant? Or the? I mean, I'm okay with it. Is the function increasing? Is the function decreasing? So it's not really, so, and it's kind of a weird thing to say. Let's go back to this graph and think about that. Okay. When you look at a graph like this, it's hard to say that it's constant anywhere, right? But remember, with derivatives, you're just looking at instants. Like, I'm not looking at an interval of any size. I'm just looking at points. So, you know, if you're looking at f prime of, oh, that is a mistake. Look, if I'm looking at f prime of 0.5, then it's not increasing, it's not decreasing. We have used the term critical point. In other, particularly in England, they call that a stationary point, which I think is actually probably a better term than we use. But yeah, it's stationary point. It really tells you that, yeah, it's not changing. So I'm okay with the language of constant, but basically, let's make it a little even more specific. Neither increasing nor decreasing. We okay with that? Cool. So let's do this example here. I want to find where this function is increasing and decreasing. So anywhere that might be happening. So if I want to look at where it's increasing and decreasing, how can I get that information? Plugging in a positive number, so like f of 2. So if I do f of 2, what's that going to tell me? Yeah. So let me just make the math easier on us. Let's say I look at f. So I know when I plug in 0, I'm going to get 5, right? Does that tell me, what does that tell me about increase or decrease at that point, though? So if I draw a graph, I know it goes to the point 0.05, but I don't know if it's doing that or that. I don't really have an idea, right? So plugging x values into the function gives me locations. Like, it tells me what points exist on that curve, but what's going to tell me behavior about increase and decrease? The derivative is what gives me that information. So from here, what's the derivative going to be? Okay. So there's the derivative. And I think now, like, if I try to find, for example, f prime of 0, I think that's a stationary point, right? All right. But I want to be more, I want to find basically, I want to say something about all the real numbers and whether it's increasing or decreasing at every real number. So what can I do with this derivative to help me do that? Right. So I think that's a good idea. So in order to find out where the function's increasing and decreasing, we're probably better off finding out where the function's doing neither and using that to get us started. So if I set this equal to 0, can I do anything to help me solve this equation? 12x factors out. So I get x squared minus x minus 2. This factors to x plus 1, x minus 2. get x equals 0, -1, +2. So that gives me 3 points to look at. Derivative of 0 at all these places. So what's really good about having those places, those stationary points, those critical points, is not only have we found the places where the derivative is equal to 0, we also, and I think this is actually at least as powerful, we found that the derivative cannot be equal to 0 anywhere else. Which means if we find positive or negative on these little subintervals, one point can tell us about every other point. So, what other points are I look at? 1 is good. What else? Negative. -2 is good too. So those 3 points should tell us everything we need to know, right? Oh, you're right. You voted on 3? Okay. So yeah, I need those 4 test points. So let's get all of them and figure out what that tells us. What is f prime of -2? What was that? Negative what? Does it matter? Are we okay if I just write this? How do we do that so fast? How do we know so quickly that that's negative? Right. So I think in this factored form is really figuring out. It's pretty easy for that too. If you let x be -2, then you're going to multiply 3 negative numbers together, right? So I agree that that one's going to be negative. How about -1/2? We're going to have a negative times a negative. Sorry, no, negative times a positive times a negative. So that'll be positive. If I plug in 1, I'll have positive times positive times negative. And finally 3, positive times positive times positive. So I'm going to pause here. We did that quite a bit more quickly than we have in the past, and we didn't get the numbers. So when you're doing this on your own, or if you want to do it right now, we can. If it comforts you, we can definitely get what those numbers really are. But any questions about how we've done this and how we've justified it so far? Do I need any more information? All right, so let's split these up into 2 sections. I want to find out where it's increasing and where it's decreasing. So what's a good set notation for all the places where this function is increasing? What was that? Right, so yeah, I'm asking how to write that. Well, I'm looking at x values. So it's not, I don't think, yeah, greater than 2 is going to be part of this. Let's go from least to greatest, so from left to right. -1 to 0. Do I include the endpoints? No. And why don't I include the endpoints? Right, so it's not increasing, it's neither increasing nor decreasing there. So from -1 to 0, anywhere else? Okay, so I think that's a good way to represent that. How about if it's decreasing? Negative infinity, -1. Heard 1 to 0, 0 to 1 as well. So yeah, it is decreasing from 0 to 1, but it's decreasing the whole interval from 0 to 2. So, and I'm glad that came up. What is special about the point? What's special about the number 1 here? Nothing really. Why? So why'd we pick it? Right. So we could have picked anything between 0 and 2. It would have been a little bit of a bad choice to choose anything other than 1. I mean, integers are always nice if you can access them. But really, that number 1 was just a good test point. You know, it is not either endpoint of that interval. So the endpoints of the interval really only come from where the derivative was equal 0. In between those critical points, the derivative is doing something monotonic. And what I mean by that, it's either increasing or decreasing over the entire subinterval. Sebastian?
Like visualize this line graph as if there were.
Yeah, let me. Here's the way that I've drawn this in previous classes, not of this class, but. So what do I know about, or the critical points are 0, -1, and 2, right? So I know the function sort of acts like this at those 3 places, right? What's going on at -2? What's going on at -1/2? Up. You know what? Let's actually put that up there then. Okay. So if it makes you feel better, that's maybe a little more graphically oriented to help you see how this function behaves. And I think doing that might even be a little more obvious as to like, when x equals -1, what kind of point is that? Local what? Minimum, right? And I think, yeah, if you draw a graph like that here, it might be more obvious. Lots of ways you can represent this. Whatever makes most sense to you is best for you. Have we said everything we need to say about this? I think we have. Any questions? We need to see a picture of it. So what did we say? Decreasing from -infinity to -1, then increasing from -1 to 0, and then decreasing between 0 and where?
2.
Okay. What's that point? Okay, good. And then increasing thereafter, right? Okay. So I think we did good. Did well, sorry. All right, back to this. So the first derivative test is, you know, we haven't really formalized it. We've just been kind of using it based on what we know the derivative does, but here's how we're using it. If f prime changes from positive to negative at c, as x increases, then f has a what? So think about what that function is doing. F prime changes from positive to negative. That's c. What kind of object is c? It's FC. So derivative is positive, so right. So yeah, function's increasing, right? And then gets to a certain point, and at that point, everywhere after that point, the function decreases. So yes, that is a local maximum. If I have the exact opposite behavior, that's a what? If f prime does not change sign at c as x increases, then f has a what? I should say that I meant to put this in there too. But f prime of c equals 0. I don't know if I told you what a possible name for these points is. You were going to say what? We call these being what I'm looking for is saddle point. Yeah, the derivative. So the function is constant there, but you know, a good example of this is what y equals x cubed looks like. Around the origin, it comes to one of those critical points, but it does not. It's not increasing or decreasing. Or sorry, it's not a local max or a local min. So that would be a saddle point. Anything new here? I mean, I was hoping this would just be kind of a way to consolidate things we've already been doing, but any questions here? Okay. All right, let's find all the local extrema on this thing. What do we need to do? Do we? This function look familiar? Yeah, same one, right? So those are the three critical points, right? Okay, so we didn't find the local extrema. We just found where the function was increasing and decreasing, right? So what do I need to do to find those local extrema? Plug what values where?
Oh, we are.
Mhm.
So, we may really go on.
That's what I'm asking, for the values of what specifically? Right, so for example, I want to find, let's say we want to focus on x equals -1 first. If I want to find the local extrema or extremum associated with that x value, what do I have to do? Okay, that's what I was, if you already said that, I'm sorry, but that was the vagueness I was trying to get around. So yeah, I'm trying to find basically where these points are. I've already figured out what I needed to know about what the rate of change was around these points, but now I want to find out where they are. So what is f of -1? Is it 0? 3 plus 4 minus 12 plus, yep. Okay. F of 0 is 5. F of 2 is -27, I'm pretty sure. Yeah, okay. So now that I have those 3 points, so now I have these points, right? -1, 0, 0, 5, and then 2, -27. What kinds of points are these? Let's start with -1, 0. What kind of point is that? A local what? What's that? And why is that? Okay, yeah, that's the information that's not on the slide right now, but our function was decreasing to the left at that point. So that's a local minimum. The 0, 5 was at a local max. I'm asking. And then this one was a local minimum. Sebastian? Mm-hmm. And this is because of intervals of decrease. Any more questions on this one? All right, now I'm giving you a closed interval. I want to find all local minimum and maximum values of this function over that interval. So if that's what I want to find, how would I find them? All right, derivative is what? 1 plus 2 cosine x. And what do I care about with this derivative? Awesome. All right, so 1 plus 2 cosine x equals 0. If I solve, best I can do right now is solve for the cosine. So cosine x is going to be equal to -1/2. So here's the thing. I am looking for all of the possible local extrema on this interval. So I could have multiple x values that make this work. But can I be more specific about that? What quadrants? So I'm looking between 0 and 2 pi. So because of that, what quadrants of my unit circle am I going to look at? Is that all? All 4, right? So can I narrow that down even more though? Sebastian? Oh, okay. Okay. So that means I can throw out, quadrant 1 and 4, right? So remember, if we're looking at the unit circle, which I'll actually draw part of now, the cosine of an angle is related to the x coordinates that are on the unit circle, right? So if the cosine is negative, that means I have to be left of the y-axis. So basically, I'm going to have an angle in each one of those quadrants that makes this true. So let's go a little deeper. I know the cosine of this angle is -1/2. So I'm looking at the unit circle. So I want the hypotenuse to be 1. And I want the x value to be -1/2. What does that mean the y value is? Positive or negative? Positive. So I guess what I'm really asking then is, what is this angle here? $60 degrees, right? So yeah, that's kind of you jumped a step I was going to ask for, but yeah, this angle right here is pi/3, right? But I'm really asking not for that angle, but this one, which is 2 pi/3. So that's one of my angles that I care about, x equals 2 pi/3. What's the other one going to be? Yeah, so yeah, one of your angles was pi, so pi/3 less than pi. The other one's going to be pi/3 more. So this other one is going to be 4 pi/3. Are there any other angles I need to look for? I'm only looking at one period. So from 0 to 2 pi, so all I need to find, like I don't need to look between 2 pi and 4 pi for example. So I have those two angles. I could have local min and local max there, but I need to make sure that I do. So how do I find out if those points are actually? Go ahead, Jordan.
You also want to test again.
I'm going to say no. How come? Why is the answer no? I mean, I don't. Yeah, you look for it. I'm saying we don't even need to go look at the endpoints. That's what I'm asking, Thomas. Right. So yeah, local. So, for example, if I have this, so I am not about to graph what this function looks like, but let's say I have closed interval between these 2 points. So this point right here would be the absolute max, but it's not a local max. So yeah, local extrema are all about all about what the first derivative is. It's all about increasing. It's all about increase to decrease or vice versa. So for that reason, we do not need to look at the endpoints here. So how can I find out? Let's just stick with 2 pi over 3. How can I find out whether that point or whether that x value gives me a local min, local max, or neither of them? Line thing is always useful. What should I populate the line thing with, numbers or slopes? Or did people not have strong feelings either way? Let's do that. So here are my 2 critical values. I know that my slope is 0 at either one of the critical values. So what are some good test points to use for the rest of this? Where did that go? I'm gonna, now let's do pi over 2. Between them? Pi is good. Pi over 2. Okay, what is the derivative equal to at pi over 2? What is the cosine of pi over 2? Okay, so I think that derivative has to be positive, right? 1 plus 0. What is 1 plus 2 cosine of pi? And then how about 3 pi over 2? What's the cosine of 3 pi over 2? The cosine of, yeah, well, I mean, the whole thing is positive, right? Yeah, cosine of 3 pi over 2 is 0. All right. So what have I learned? I have a local max where 2 pi over 3, we're going to leave this blank for now. But for now, we can definitely say that we have a local max at x equals 2 pi over 3 and a local min at x equals 4 pi over 3, right? So now we just got to figure out the rest of that story. So how would I find the rest of my local max point? Yep. So let's find f of 2 pi over 3, and that's equal to 2 pi over 3 plus 2 sine of 2 pi over 3. Good thing we drew a diagram. What is the sine of 2 pi over 3? Root 3 over 2. So this comes out to be 2 pi over 3 plus 2 times radical 3 over 2, which is radical 3. I'm going to just do that as is. All right, similar thing for f of 4 pi over 3 equal to 4 pi over 3 plus 2 sine 4 pi over 3. What's the sine of 4 pi over 3? Negative 1. Negative root 3 over 2. So then this would be 4 pi over 3 minus radical 3. Any other questions about this?
So, is there ever a circumstance in which the endpoints or the absolute maximum minimum are considered local?
Yeah, I mean, for example, if I altered this interval to be 0, 4 pi over 3,
Mhm.
you would have an absolute max and a low, or sorry, absolute min and local min at the same place.
So when do you include the absolute max in the interval?
That's a good question. So let me erase the interval I just made. So looking at the base of the problem I gave you,
Mhm.
what's one alteration I could make to this problem statement that would require us to look at the endpoints of the interval? Yeah, so I could either replace this with the word absolute, or I could replace it with nothing. So if I'm looking, so moral of the story is the only time I'm looking at the endpoints for anything is if I'm looking for absolute extrema.
Okay.
And just to go back to the definition, the absolute min and max happen where, so I'll just say with the maximum. The absolute maximum happens, where the function takes its greatest value. And the function can take its greatest value either at these critical points or at the ends. But the local max only takes place at critical points.
Right.
Good question. All right. Do we need to see it? Yeah, let's look at it real quick. So we were only looking from 0 to 2 pi, right? We found this point, 2 pi over 3, and then probably what we had. And then, 4 pi over 3. So local max, local min. So looking at these two things, now we're going to move beyond the first derivative. But first, let's just talk about the first derivative. What can I say about f prime of x for both of these graphs? F prime of x is increasing in both of them? Okay, I will definitely say that this is true. F prime of x is positive, right? Okay, so that's just a thing to pay attention to with the language. Big difference between saying something's positive and saying something's increasing. Same what? Would f have the same average or would f prime have the same average? They're not going to have the same average. So yeah, f prime is not going to have the same average. I think f would, but I can't say that about. Actually, can I even say that about f and g? No, I couldn't say that about either one. So let's go back to the idea of increase and decrease here. Is f prime of x increasing? Okay, so we're saying this is true. F prime of x increasing. Why do you say it's increasing? Okay, so and there's a couple big distinctions to make there. Clearly, f is increasing, right? Because if I were to draw tangent lines anywhere on f, what tells me the function is increasing? So the fact that the reason we know that f prime is increasing is the fact that if you go from left to right, as you go from left to right, your tangent lines are going to get steeper and steeper, right? I should pause there because that's a subtle yet important difference. Could I say that g prime of, or we already said g prime of x is greater than 0? Is g prime of x increasing? If I were to draw a tangent line here, it'd be pretty vertical. Over here. So look at what's happening with the tangent lines as I move to the right. What does that tell you about g prime of x. Good. So G is flattening out and approaching the saddle point or a critical point. But what is G prime doing? It's decreasing. So, and like let's talk about that because now we're getting into the territory of second derivatives. So that increases because these slopes are going to be strictly positive. So now where I draw why is that drawing increasing? Like that. All right, so let's apply that same law. Yeah, same idea since the slopes are positive. So the first question I asked you when you came in was, what does the derivative of a function tell us? And you said a couple of things, the instantaneous rate of change and the slopes of the tangent lines of that graph. We can't really use, so if we're gonna talk about the second derivative, we can't really talk about the slopes of tangent lines because we're not graphing the first derivative here. Let's talk about instantaneous rate of change. And let's be more specific about what the rate of change is. F prime tells you the rate of change of what function? Of f, right? So f double prime tells you the rate of change of what function? Not f, but f prime, right? So f prime is the first derivative of f. F double prime is the first derivative of. So no matter what the derivative is you're talking about, it tells you something about, you know, the order, the function that it came directly from. Sebastian? It might not be linear, but f prime will be positive. I think you're assuming it's a parabola. So, first thing, the right way to explain this without getting really stuck in the mud. Yeah, that's why I think you're saying that, is because gravity is a so yeah, we're talking about parabolas, and that's how we'll set it. I'm not guaranteeing you these are what. That's why I can't say things. I can't say things that's wrong. Yeah, I mean, yeah, should be parabola, it might be something.
Is it the second derivative that shows concavity?
Yeah, that's really one area, but for now, what I want to focus on the second derivative says something about gravity. So let's go back to this idea. And what does that mean about the second derivative? It's positive. I can't say the second derivative is increasing, but I can certainly say it's positive. What's true of G double prime? Well, G prime is decreasing, right? So what does that mean about G double prime? It's negative. And let's just relate that to what we've talked about, you know, just function in its first derivative. If the function f is increasing, all you can tell me, let's unless I give you more information, is that the first derivative is positive. So let's try to look at least one, or let's go a little further. So I don't want to leave you there. So let's talk about this issue of concavity. Sorry. So basically, concavity is, by definition, tied to this idea of a second derivative. If the second derivative of a function is positive for all x on some interval, then f is concave. And when f is concave up, what we just talked about is, if f double prime is positive, then what's true about f prime? It's increasing. So you have a function that, so if f prime is increasing, then what's f? Actually, take it back. I can't answer that question. Because it might not be shaped like that. So I got a graph to show you. Let's talk about the concavity on a couple of intervals here. Actually, one more thing for you. If the second derivative is equal to 0 and the concavities on either side are different, then you have what's called an inflection point. So I'll come back to this when you're on your way out, but I wanted to, where's my, here's what I wanted to look at. So let's just do a couple of these intervals and we'll save the rest for next time. So, you said two things. One of those is true. Now here it's increasing. So I'm going to say that f prime is decreasing. What's a good graphical way I could say that for sure? If I draw the tangents, this one's going to be steep. This one's going to be less steep. This one's the kind of the smoking gun. That one's going to be about 0. And this is even more drastic. That one's going to be negative, right? So your first derivative goes from steep, less steep, 0, negative, right? So that tells me the first derivative is decreasing over that interval, right? So what does that mean about f double prime? So what does that mean about the concavity of this function over here? Concave down. So I'm glad we did one interval. I'm gonna stop there. We'll chop up the rest of this thing on Monday. You wanted to look at this slide. I got quizzes for you if you want to stick around. Otherwise, I'll see you on Monday. Thank you.